Happy December 9th. I'm going to mention something to do with the number 9. Now, earlier on in the month, I talked about things like the Higgs boson and how discovering the mass of the Higgs boson tells us everything we need to know about the Standard Model, and then made a disclaimer about neutrinos. I also talked about the CKM matrix and how that gives us more matter than antimatter in the universe. Now, what I want to talk about today is the equivalent of the CKM matrix for neutrinos. It's called the PMNS matrix, and I can't remember what the names are, I'm afraid. Now, neutrinos are very mysterious particles because they very, very rarely interact with matter. They have almost no mass and they have no charge, and that makes them very difficult to detect. And because they're very difficult to detect, it takes us decades to make any kind of progress with these particles. They basically get produced every time we have a sort of weak force decaying particles. It will usually produce a large number of neutrinos when this happens. So for example, in the Sun, we have fusion taking place that produces lots of electrons and lots of neutrinos. And the electrons get stopped in the Sun, but the neutrinos, they fly out through space. And that means there's this constant background of neutrinos that are passing through us all the time unnoticed. In fact, it would take about 4.2 light years of water before a neutrino would interact. It would travel through 4.2 light years, and then you'd expect it to interact on that kind of length scale. Now, why are neutrinos interesting? Well, the reason they're interesting is because the neutrinos come in different flavours, electron, muon and tau, just like the charged leptons we talked about a few days ago. But the thing is, you can produce a neutrino in the electron state, you can follow it for a while, see it interact somewhere else, and it can change flavour into the muon state or the tau state, or even change into one of those states and back to the electron state again. Now this is known as neutrino mixing. Now the only way that neutrinos can mix is if they have mass. And if neutrinos have mass and they mix, there's a potential source of CP violation there. And that can give us more insight into the matter-antimatter asymmetry in the universe that we see around us. So we have these neutrinos with masses, and we have these new mixing parameters, and we can make our new matrix, and we can even make the equivalent of the unitary triangle. But it's extremely difficult to measure. Some of the results that came out this year included the result from Daya Bay that measured one of these mixing angles, theta 1,3, and they said it's not zero. And that's very interesting because that favours some models over some other models, and it tells us a bit more about how these neutrinos interact. It gives the neutrino mixing matrix space to have a complex phase, and when you have a complex phase, that leads to CP violation. So these neutrinos, extremely difficult to detect, extremely difficult to measure their properties, are telling us something very fundamental about the universe. And so we're going to see more discoveries come out about the neutrinos in the coming decades. It's going to take a very long time to get the data we need, but when we do, it's going to tell us something very deep about the matter-antimatter asymmetry in the universe around us. And that is why neutrinos are cool, and that is why the Higgs is not the end of the road, it's not the final say in the Standard Model. There's this other thing happening with neutrinos that goes beyond the Standard Model, and we can't incorporate it into the Standard Model until we understand it properly. So keep your eye on neutrinos. They're going to be showing us some really fascinating results in the coming years and decades. Okay, I'll see you tomorrow.